Our first speaker is Mustansi Barma, and he's going to talk about stretched exponentials, power relaxation. Mustansi.
Thank you. Start? Yeah. Okay, thanks a lot, organizers, for inviting me to this meeting. RRI has, of course, a long tryst with statistical physics, mainly due to the efforts in those days of Sanjay and Abhishek together. They started the RRI school, where, I don't know, I'm curious later, I'll find out how many of the audience, were students there. And that was a great series. It has continued in some form or the other as the Bangalore School on Statistical Physics. And I think that's been one of the very important activities which has gelled a real community of statistical physics in India. So, yeah, so I'm glad to be here for that reason and for, of course, for the conference, yeah. Anyway, so today I'll talk about, question which is a little old, We're talking about stretched exponential decays and power laws and actually crossovers between the two. And the main thrust of the talk is I'll discuss two quite simply defined models which are kinetically constrained, which I'll define that, where you can work out, and by work out I don't mean analytically solve, but you can actually understand the mechanism for the crossover from stretched exponential to power law, which apparently happens in, several systems. So that is the plan of the talk. Okay, my collaborators in this work, so all this work was done at TFR Hyderabad, and Puneet Parikh, who is a PhD student there working with Saroj. Sukanta Mukherjee was a visiting student, now in Dresden. Vaibhav Gupta also was a visiting student. Now he is doing a PhD at the University of Illinois and in Urbana-Champaign. And of course, Saroj, who's a faculty member at TFR Hyderabad. So these are the collaborators, and let me now begin. Okay, just as an introduction, slow decays are sort of ubiquitous, we know that. And they occur in lots and lots of contexts and systems. And they can arise from, let's say, conservation laws, criticality, power laws, that is. And if you come to stretched exponentials, you can think of many mechanisms. Something that was proposed many years ago by Palmer, Anderson, and collaborators was this idea of hierarchical relaxation, namely the idea that normally a single mode will relax exponentially, but if there are constraints which let one mode begin to relax only after another one is completed, then you can overall generate slower decays, stretched exponential being typical. Kinetic constraints, which are constraints on microscopic moves which define your dynamics, which is typically stochastic. I'll talk about that. FDPO is another example which generates, if you like, stretched exponential-like behavior. FDPO stands for fluctuation-dominated phase ordering. So, sort of state that happens in many non-equilibrium and now also found in equilibrium systems. Right, so this is known, but the question I'm going to address is really about crossover. So there are some systems, which start out decaying as a stretched exponential, and at some time there's a crossover time, after which the decay switches to something even slower, namely a power law. Now, this is known in some simulations and claimed to be also in some experiments. And let me show you a couple of examples that Saroj told me about. So this is a simulation for active colloidal glasses. And you can see the crossover here, there's a fairly rapid crossover. This is a fit to e to the minus some t to the alpha. Alpha in this particular fit is about 0.38 or something. And you see that if it had continued, it would have gone this way. It doesn't. The actual system slows down and settles into a power law decay. Similarly, in polymer chains dynamics, actually I don't know much about the actual system in this case, but there's again evidence of a crossover from stretched exponential to power law. Okay, so this is like a slightly motivational slide. I mean, this happens. So are there simple systems in which it also happens and where we can understand better why it happens? That is the idea. All right. So I'm going to so here is what I'm going to do. I'll investigate this sort of behavior in two models. Both the models have kinetic constraints, which is what I said that, for instance, if you have a spin system and you have a Glauber dynamics, so you can flip spin up to down, but you can do it only if something, 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 only if the neighbors are like this or something or the other happens. So that gives you a constraint, and constraints normally will slow down things. So that is what is happening here. So the first model I'll talk about is a model which talks about domain walls. Domain walls, of course, is a very familiar concept. It's a separator between two types of ordered regions, let's say up spins, domain wall, down spins, etc. And often in models that we encounter, domain walls diffuse. So what we'll argue is that this is actually what happens. Domain walls do diffuse, but they form bound states. And when they form bound states of a certain sort, the pattern of relaxation actually changes from stretched exponential to power law. So the point is the following. The domain walls are diffusing, but they're diffusing the domain walls. They're not the primary entities in a sense. They're spins. And we're interested in the spin-spin autocorrelation function, which will activate when the domain wall sweeps across. So although the domain wall is moving diffusively, it generates a spin-spin autocorrelation function which decays as a stretched exponential. Okay, that was the first one. This is known. This is known for a long time. But in addition, what I'm saying is that there is a binding of domain walls, which I'll explain why. Very simple. And that binding then leads to a change of the pattern of relaxation. Okay. How does it, what is the model and what happens? Okay, that's the first model. The second one is a much more familiar scenario. I mean, you think about a system at very large temperature and you quench it to 0 temperature. The system we are interested in is actually the Annie model. A-N-N-N, lots of N's and one I. Okay, right. And the point about quenching to 0 temperature is that you start with a very disordered state, but you come to a state which is 0 temperature, so you don't allow energy raising moves there. Okay, so because the temperature is 0. So in that case, what we'll see is once again, a similar scenario arises, but the reason for the change to the power law is quite different. It has nothing to do with the bound states or anything. It's just that taking a simple ensemble average over initial states changes the pattern. So let me proceed and try to argue for these. Okay, so here is my promised kinetic constraint. It's very simple, and you must have encountered, many of you may have encountered a similar constraint or imposed a similar constraint in other contexts. And the constraint is simply that a spin, the red spin shown here, can flip only if its neighbors are oppositely oriented, up and down, or then this can flip to down and back similarly down and up and back. So you will recognize immediately that this move will lead to a domain wall moving. Okay, unfortunately I didn't make a picture of this. And I don't see a blackboard. What shall I do?
There's a blackboard.
Oh, there is a blackboard. Okay. Right, yeah, thank you. Okay, thanks. Okay.
I missed something. Are you only looking at one dimension?
Yes, yeah, I should have said that right in the beginning. I'm looking at one dimension. Some of the things I say will apply higher, but 1D. Right, thank you. Right, so here we are with a bunch of upspins here, and then, so here are your, so the only spins that can actually flip are this and that, and there's a wall in between. Only spins that can flip in view of my constraint, okay? And when something flips, the domain wall moves. It moves equally likely right or left, and therefore you can think of it as performing a random walk. So what happens is that these domain walls, there could be many in the system, all perform random walks with a hardcore constraint. Okay, why a hardcore constraint? Because if you narrow down to a single upspin, in a downspin matrix, we are not allowing energy lowering moves here. If you could lower the energy, these domain walls would annihilate. This is the familiar process for coarsening in a one-dimensionalizing model, but this is forbidden here. We are working in a strictly microcanonical system, microscopically microcanonical, where the energy is fixed, the Ising energy. So we don't allow annihilation. So all they do is that they move around and they bounce around, and this is a well-known and well-studied system, the simple exclusion process. And that's what the domain wall dynamics is. Question, what is the implication for the spin-spin autocorrelation function? Turns out this question has been studied many years ago by a person named Skinner in the context of polymer physics, and more carefully and quite rigorously by Herbert Spoon. I thought he may be in the audience, but oh, he's coming tomorrow. Okay, good. All right. Anyway, so there's a very nice paper by Spoon in 1989. I find it a little difficult to read, and I can't understand everything, but it's like that. But there are rigorous results, and a single rigorous result is worth a lot. So so I would, I'll at least what should I say? Tell you what the result is. All right. So, but there's an intuitive argument which is also sort of given in a few lines in the paper. So let me give you that argument. So let's think about it. So here are your red domain walls. They're moving all over the place. But we are interested in this autocorrelation function here. So here is a site, and we want to know how the spin is changing in time. And it will change every time any domain wall crosses it. Okay, so this is the sequence of up and down things that happen as a function of time. All right. Now, so how do we think about it? So suppose there's a very large domain, length L, maybe exceptionally large, it doesn't have to be, but okay, let's say exceptionally large. And you are a spin in the middle of this domain. Now, you want to flip. You can't, because of kinetic constraint. You have to wait for the domain wall to come in. But how long will it take? That is what we ask. And the rough argument is the following, that the domain wall, you look at it hopefully, but it's coming, but it's diffusing. It's not coming one way. So it will take a time of order L squared, to reach you if you're in a cluster of size L. On the other hand, the probability of occurrence of a long stretch of size L is exponentially small. In fact, for this particular model can be worked out very correctly and easily. In other words, psi is known from transfer matrix or any other method. But put these together in some undefined loose way, and you say that, okay, you expect this spin-spin correlation, autocorrelation, the spin in the middle, which was waiting for the domain wall, will decay as, well, this L goes into T to the half. And so this is how it may decay. Beg your pardon? At the bottom? Yes.
But you are working at 0 temperature, is it?
No. So there are, yes, so as far as the Ising, well, how would you say it? I'm just imposing a kinetic constraint. See, where does temperature enter? It enters into the fact that when you have okay, let me go back if I could. So when you have this spin flip, how will you decide the rate of flip? You'll decide it through temperature criterion, which is, so this is not at 0 temperature in that sense.
Also, your energy is conserved, so there must be initial condition, whatever energy that corresponds to some temperature, I suppose.
Yeah, exactly. I mean, that's right. So if you think of that energy as an internal energy of the Ising model, you can associate a temperature with that, correct? So if you like that is a good way to think about it. It's the energy associated with your particular initial state. That's right. Okay, so what did Herbert Spoon do? He proved upper and lower bounds on tau. In other words, the relaxation rate. So I will not tell you how he did it because I don't quite understand how he did it. But they're very concrete bounds. Here they are. Here's a formula. The lower bound is more complicated, and there's a large expression you have to optimize or minimize in order to find the bound. And he writes in the paper that he thinks, without proof, that the lower bound is actually exact. But okay, whatever. My point is that there are bounds, lower and upper bounds, and therefore this form is correct. It is stretched exponential, there's no doubt about it. Okay, right. However, the model I'm going to deal with is a slight variant of this model. It's a very small variant, but it's an important distinction. And we came up with this model with some motivation and history from Saroja's background and glasses and so on. But we called it the domain wall to double-on model. And we put it on ConMat archives. And next day we got a mail from Professor Garahan pointing out that the same model has been looked at by him and co-authors a few years earlier. And it was called the XOR FA model. The FA model is the Fredrickson-Anderson model, which is a well-known kinetically constrained model in the glass and other literature. And this is a variant. And the variant, along with this, it's identical to the DWD in terms of definition. But so let me proceed and define the model. Whether you call it DWD, which we do, or XOR is up to you. Okay. What is the model? The model is very simple. It's the same as before. The constraint is the kinetic constraint, except that we're thinking now that we have a field, a magnetic field, okay, of the order of temperature. Okay. I haven't put H, for some reason we called it 1, that field. And notice the sign, it's a negative field, so it prefers downspins. Okay. All right. Since you have a field, the domain wall here between a stretch of ups and downs will not move equally likely right or left. It will move more likely into the upspin stretch than down, simply because if you do that, you increase the number of downspins, and that is favorable with the energy that I have. Okay, so you can write down the dynamics that goes with this. Right, so this is the way we imagine the model. Now, just to tell you about Garahan et al.'s motivation, I mean, again, I don't know the experiments much, but you know there are Rydberg atoms, and if you have a line of atoms which are potentially in a Rydberg state, the Rydberg states are so big that they can block what is going on in the state in atoms next by, and this is called the Rydberg blockade. Now, sometimes it can happen, as argued by these authors, that you can actually promote the next atom to a Rydberg state only if the nearest neighbor is Rydberg, but not the other. Okay, so that you can immediately translate in your mind as Rydberg being spin up or spin down, and giving you exactly this kinetic constraint. So, however, I mean, the focus of these two papers is completely different. I mean, Garahan et al. Are interested in the bunching of trajectories in extended space-time, and looking at the characteristics of that, and perhaps transitions as a function of parameters in the degree of bunching, whereas we are looking at simply spin-spin autocorrelation functions. Okay, so this is the dynamics. Now, what happens with this dynamics to the... Well, what happens is quite dramatic, as you can see from this picture. See, first of all, as we've said, domain walls move so as to shrink the up domains because of energetics. And so in some sense, this domain wall and the next one, there's an attraction, because both tend to go in. So in some sense, they can form a bound state. Do they actually do that? Look at this simulation. And what you have is space and time. And so we have 4 domain walls in this picture. 1, 2, 3, and 4. Or was it 3? Yeah, 4. Okay. And you let them loose. Here are upspins. The gray is downspins. And you see that these walls move into the upspin thing. Then they form something very tight. And that tight entity moves around. So this is the doublon that we are talking about. It still has 2 domain walls on its sides, but they're very close by, 1 or 2 or 3 lattice spacings. So from far away, these domain walls have come, bunched, and now they're moving together. Okay, so here is a blow up of this something along one of these trajectories, and you can see what is happening. There are 2 domain walls. So this doublon is not fixed in size. It can fluctuate, but not much. I mean, the force is very strong. It's a confining force, and it comes back. Also, if you have 2 doublons, they can't do, I mean, they repel, because they're made of domain walls, and domain walls have repulsion. So doublons also have hard coil interactions. Okay, so this is the phenomenology of the model, right? Oh, I went back. Exactly, it does, indeed. That's right. So you started with symmetric exclusion process of domain walls. You end up with symmetric exclusion process of doublons, in a sense, almost that. But they have profoundly different effects on the dynamics, because let's look at the second regime first. Doublon is basically an upspin. I mean, localized bunch of upspins. So it's just the spin-spin autocorrelation that decays diffusively. That's the power law. Earlier, you had domain wall diffusion, but that's not the same thing. That generates a stretch extension. So you figured it out. That's all that's happening.
I thought you had asymmetric exclusion because of the fill, right?
It's asymmetric in a way, but it's not the normal one. So 3, 4 domain walls. So these 2 will attract, because there's upspins here, then there's down, then these 2 will attract. So it's a pairs. So the pairs nicely pair up, and then they move. Okay? So that is what is happening.
And where is the kinetic constraint?
The kinetic constraint came in right in the beginning, even for the domain walls.
Just that the energy is
Yes, exactly. The energy strict microcanonical, well, yeah. So think about it like this. There was a giant J, Ising J, okay, and that you are conserving strictly. But now you put on a small field H, which is possible, and you can ask what is the effect of that. That's what you're asking. So both temperature and field are much smaller than J. J you cannot override. That is your constraint. Okay. Right. So, so if you have a single domain wall or a single doublon, you can actually calculate its properties quite easily. And so I've written down the drift velocity of a single domain wall as it's moving into this. And here is the diffusion constant associated with that, with some parameter C, which depends on the temperature. So these doublons, on the other hand, perform unbiased random walks. So here's an extreme doublon, extreme meaning very tight. It's only one spin. And how can it move? Well, it has to wait for one of these to flip. But if that flips, then this domain wall can slide over again. So it can generate a single move quite easily. Okay, I mean, if you want, I will demonstrate it, but I won't do it right now. Okay, and the diffusion constant is therefore quite low. I say low because C is e to the minus 2 by t. So as t goes to 0, this becomes very small. So it's a small diffusion constant of the doublons. Look at these data. We're just monitoring a single domain wall. A single domain wall. You label the domain wall and look at it. And look at x squared. Okay, it's increasing nicely, diffusing. Then crash, it goes down because these two domain walls have met. This and that. So suppose I'm monitoring this. Here it is, it's going nicely along. That's your initial slope. Then out of nowhere came the other domain wall. So, violent interaction. This comes down, okay, and then increases again, but with a much reduced slope. This slope tells you the diffusion constant of the doublon, because as the doublon is moving, naturally the domain wall that makes it up is also moving. Okay, so this is what is going on. All right, how am I doing for time?
So you have about 20 minutes.
Okay, good, very good. That's more than I thought I would. So
15 minutes.
yeah. Yeah. Now that reminds me of a talk I gave at ICTS some time back. They had a timer which shows you how much you have left. I thought that's how much I finished. So when it showed 10, I was very happy. Anyway, so that was one domain wall, but what happens with a very large number? Well, a very large number actually shows this crossover that I promised. Here is temperature equal to 1. And it's a, very, I feel, convincing changeover from stretch exponential to power law. This is data for many temperatures. Low temperatures here, high temperatures there, and replotted as to bring out the stretched exponential character here, plotted against root t semi-log. This was log-log, semi-log, and you see a straight line. That straight line is the stretched exponential. So what is happening is very simple. I mean, indeed at short times, so suppose you're at very high temperature. The bias is small. Okay, that little c, which was measure of the inward movement, is small. And because it's small, it takes some time for it to get recognized. So in the beginning, there's simple diffusion of domain walls, and that generates the stretched exponential. At some point, these form and collide, and diffusion of the variety that they talked about happens, and that's all. Right. So, right. So, yeah, just one remark that this stretched exponential form holds very cleanly, and it should, at high temperatures, because in the limit of infinite temperature, you recover the symmetric case. At low temperatures, it's much less clear what is happening, but let me, yeah, I mean, it's clear what is happening. You are forming these bound states, but you may not have a very good stretched exponential region before that. So in fact, if you look at the crossover time, it's non-monotonic as a function of temperature. So the easy part to understand is the high temperature part, because this just reflects the lack of bias right here, and the bias is increasing as you lower the temperature. This rises simply because all dynamics slows down. At low temperatures, because of the Boltzmann factor, everything slows down, and including the crossover time and so on and so forth. And this is what happens. So as a test of that hypothesis at low temperatures, if you define a pseudo time in terms of accepted moves only, then indeed you recover monotonic behavior. Okay, so I think with that I conclude the first part. Yes.
So what is this characteristic temperature at which the minimum occurs?
It's of order 1, but I don't remember the exact number.
But there's no physical meaning of this temperature?
I don't think so. The reason I don't think so is that when you do it in terms of the pseudo time, there is no minimum. It just goes smoothly. But I'm not very sure. I mean, I'd be happy to get a suggestion. Yes. Yeah, yeah. What I'm saying is that it takes longer. So what should I do? Previous? Right. Yeah, yeah, yeah. By a faster relaxation, but we don't know what it is. Earlier we thought it may be stretched exponential, but it may not be. It's just faster than power law. Faster than power law. But so numeric, I mean, we don't have a theory for it, and well, yeah, it may be just exponential. I don't know. That's my guess. I mean, yeah.
In fact, if you follow this heuristic argument that you gave for this
Yeah.
calculation, so you say that e to the power minus L is the domain length.
Right.
And if it's a bias, it's
Yeah.
ballistic, so L is of order T.
Yeah.
So I would guess it would be probably exponential decay, right? It's sort of just exponential.
Yeah. I think so. Maybe not only from that, but also there's a prefactor, which I'm neglecting. So also from the prefactor, yeah. Thanks. Which I neglected in the argument, yeah. Okay, so let me march on. Okay, the last thing. Okay, very quickly. In the extreme low temperature limit, I mean, T close to 0, the doublon is very tight. It just consists of one upspin. Now, if you just follow, all the rules that I put in, two doublons cannot be closer than 2 lattice spacings away. So that suggests that maybe it's like dimers. And indeed it is. I mean, if you just work out everything, configurations, moves, etc., it's just the dimer problem in 1D. Hardcore dimers of size 2. So they're moving around doing exclusion process. Okay, dimer exclusion process, all right, okay. And which is very plausibly, I don't know if there's an exact solution to that problem, I don't think so. Very plausibly the same power laws as for the simple exclusion process. So that is why we have this. So there's an exact mapping in this limit. Yeah, okay. Good, so now let me come to the rest of it. and I see I don't have that long a time. Yeah, I just noticed the clock. But I think we will manage because the story is simple. Okay, so let's consider the Annie model. Except I'm making, often it is formulated as competing antiferromagnetic interactions. I'll make the first interaction ferromagnetic, which doesn't have much, I mean, you can translate easily to the antiferromagnetic case. So the point is, of course, that as you, if you were to do this protocol that I described in the beginning, namely quench from infinite temperature to 0 temperature, you will land up in very non-equilibrium states. In fact, they are arrested states. They are states which may evolve within a certain subspace, but are very strongly constrained. Now, what are these states like? That depends on the ratio of J2 by J1, and here is an axis which shows little J2 as J2 by J1, and there are basically 5 types of states you can land up with depending on the strength of J2. Now, I didn't tell you what the dynamics is. The dynamics is actually quite simple. It's just that 2 ups can go into 2 downs and 2 downs can go into 2 ups. Now, you might think this is slightly strange dynamics, but okay, if you want to view it in some other way, change all your spins on one sublattice, reverse them. So you have antiferromagnetic interactions here, and this move will become a simple Kawasaki move. So it's a reasonable dynamics. Okay. Now I'm going to be interested in one of these states, and let me point out which one. This one. This is the only one you see with a lot of moving domain walls. So, earlier we've investigated some of the others, but this is the one we were interested in. So let's see what happens. Okay. All right. So this nicely colored picture shows you what is happening. So you have lots of domain walls in the beginning, these goldenish objects. Okay, they move. But then you see some of them are annihilating. Yes, they are. Some are annihilating, but not all. So the dynamics is such that it generates annihilation of quite a few of the domain walls, but you are left with the residue which is conserved. Okay. It's very easy to show that you will have a conserved number. Maybe it will be on the next slide, but okay, just wait for a minute. So the coarsening, yes? Yes, in this case, indeed, this is not a kinetically constrained model yet. So we are going with strict Ising model rules, and so energy lowering moves are allowed, as are energy equal moves. No energy raising moves. Yeah, so we had 0 temperature, that's why. Okay. So these annihilation events, in fact, represent energy lowering moves. So during coarsening, there's a lot of energy lowering going on. It anneals out many of the domain walls, but you're left with some. In the steady state, those some actually again do pretty much, not exactly what I said, that the domain walls wander with a hardcore interaction. Okay, so let's see. Energy raising moves are not allowed. Yeah. So, yeah, this is the answer to Supriya, right. Okay, domain walls perform random walks, annihilation, etc., etc. You can work out from the kinematics, from the energetics that the closest approach of domain walls is 3 lattice spaces. Okay. Now, suppose you believe this, that this is actually what happens. First thing is, how many domain walls are there finally in steady state? Well, there's one obvious conservation law in this system, that is the sublattice magnetization. Because 2 up go to 2 down, MA minus MB is conserved. Now, it's easy to show, I won't show it now, that the sublattice magnetization is equal to the number of domain walls in steady state. Okay, we'll have to see why, but maybe we won't. And since we started out with the disordered state, the number of these is order square root of L, system size, right? So this sub-extensive number of random walkers has very important consequences. For instance, so the domain walls are exclusion process-like objects, except they are, what should I say, very far from each other. So as a result, if you look at the spin-spin correlation function in real space, in the steady state, it falls exponentially, but with the root, 1 over root L. Okay, let's move on. Okay, so this very colored picture is the coarsening. And the whole point is the following, that, look, you have domains. If you have a domain with an even number of spins, then you'll kill it. If you have an odd number of spins, you can't with this dynamics. So you might think, okay, so even, odd. But then you have to be careful, because there could be even, odd, even. And you, or maybe, I mean the other way, odd, even, odd. You get rid of odd, even, odd, and you get rid of the evens. And then you have two odds, that becomes even again. So the coarsening is a little more complicated than it might seem at first sight. But what survives in the end, for sure, and has to be, is only domains with an odd number of spins. Because if they were even, they would go. All right. So, so in the usual spirit of coarsening, let's think of time-dependent length scale script L, okay, which should grow like t to the half, because after all, the dynamics is diffusive. On the other hand, we derived, or we argued for, in fact, this is strictly true, you can prove it, this form in steady state. Now think about steady state to coarsening. Simple ansatz, which usually works, is that if you replace the system size by the relaxed time, relaxed size L of t, you should get the right answer. And you do. But the answer gives you a t to the quarter, therefore. So here it is. So when you substitute into, because of this extra square root, you're generating a square root of this L, which gives you t to the quarter. Yes, yeah. Okay, so I will rush ahead. And there are very interesting events which happen, which we've labeled as A, B, C during the coarsening, which we can understand each and every one of, but we won't bother with that. But here is some numerical confirmation of collapse, especially at larger times, with t to the 1/4. Okay, the last thing I wanted to say, so then what do we have? We have this diffusing domain walls with a hardcore constraint. We know already from Spohn and the earlier part that the answer is that there's a stretched exponential behavior. Indeed, that's what it is, except that the stretched exponential is unusual in that the tau depends on system size, which it will, because the number of domain walls is sub-extensive. All right, so we call this behavior size stretched exponential. All right, so it decays as an exponential, but in this way. All right, now the last bit, which came as a bit of a surprise for us. That answer I showed on the last thing is actually correct and pretty, I mean, I would say absolutely true for a single initial state. If you start with an initial state, everything is fixed. The number of domain walls, and you get this answer. However, suppose you now average this over the ensemble of typical initial states at very high temperatures, disordered states. You can't control, there's a Gaussian which controls the number of domain walls. Okay, so we take it. You have a Gaussian, if you have a Gaussian, you have to have a Gaussian, P of n. There it is, it's a Gaussian. But let's consider taking this squiggly bracket is average over initial states. Let's perform this because it's all relatively easy. So you do these, so you have to integrate over n, which is easy to do. Answer is this form which involves an error function. Okay, fine. It turns out, I mean, this was pointed out to me later, that this is a Mittag-Leffler function. Okay, I'd encountered the name of Mittag-Leffler in complex analysis, but I didn't know there is a whole series of functions, that are called Mittag-Leffler functions, and this is the simplest of those. It's with index half. Otherwise, it's defined as a series, and one doesn't have such a neat formula. But, what are its behaviors? At short times, it's 1 minus something, which is exactly the stretched exponential sort. At long times, it's a power law. So Elie Barkay is somebody who has worked a lot on Mittag-Leffler functions. And, one of the best introductions to Mittag-Leffler, I found is in one of his papers with Metzer and who was his other collaborator? Klafter, yeah, thanks. Yes. Anyway, but fine. So here's another place where this crossover occurs, but for a completely different reason, nothing to do with, So with that I'll end. I'll just say that there were two models. Both showed a crossover from stretched exponential to power law. The reasons were completely different. Thanks.
Okay, thank you, Mustasi. Questions? Kavita?
Yeah, this is interesting that figure that you showed in the first part, in which there were lots of domain walls and then just two trajectories we see.
Yeah.
So then if I look at the domain wall density, how that's changing with time. So is it changing like discontinuously, like in each realization?
No, the domain wall number is conserved, but so it's in some sense the number of diffusing objects is halved. Earlier, every domain wall was diffusing. Now we have an equal number of domain walls, but they're bunched two at a time.
Remember, domain walls is conserved.
The number is conserved.
Yes, sir.
I was wondering whether it would be possible to see that crossover also in a kinetic equation, like suppose we are studying Cahn-Hilliard equation or any other type of coarsening dynamics equation, whether one can in a unified way, by adjusting certain diffusion constants, see that transition that you're seeing in these models?
Well, there is a unified description, maybe not applicable to the models I'm talking about, where in a general way you see a crossover where you generate these Mittag-Leffler functions. And that is the formalism of fractional Brownian motion.
Okay, but that's still on the stochastic level, is it? Like
at the stochastic level.
But not on the Cahn-Hilliard type of...
Yeah, there I don't know of any, and it's an interesting thought. Maybe there is.
Perhaps it should. I don't know.
Tell me later. Yeah.
Other questions?
So in self-diffusion in liquids,
Self what?
diffusion in liquids, or the velocity autocorrelation function.
Right.
This crossover has a different explanation in terms of...
Does it happen, first of all?
Yeah, so you have long time tails.
And is it stretched exponential before that?
It can be, I suppose. Depends on the correlation function you look at, but the long time behavior...
So you're saying long time
power
tails
law,
in liquids is another place where you have power laws eventually.
Yeah.
Then maybe something.
Yeah,
Okay,
so
good.
this
Thank
is
you. Yeah, I didn't.
not a related explanation. So.
Yeah, so far everything is different. So one more.
Yeah, just to make sure that I understood the last point correctly. So the point is that the stretch exponential decay of a single sample depends on the number of domain walls,
Yes,
and that's
absolutely.
a random quantity, right?
Yeah,
so you have
that's
some
correct.
samples which have very few domain walls and therefore decay very slowly.
Yes,
And when you average,
exactly.
you get the power law. But
Right.
that means if let's say experimentally, so to speak, you would never observe that power law.
Well, it depends. If you had a microcrystallite with many different sizes,
Okay.
Yeah.
Okay.
Okay,
Yeah.
but you're right. In a given clean sample of the
Yes,
sort I'm
yes.
talking, you will never see it.
Okay.
But yeah.
there other questions, comments? Okay, so if not, let's start with Sasha
Oh,
again.
because the wrong thing. Yeah,
Yes.
thank you. Thanks.
Okay, so our next speaker is Rajesh from Institute of Mathematical Sciences in Chennai, and he's going to talk about large deviation functions in aggregations.
Many thanks to Sanjeev for organizing this wonderful meeting. So I'll talk about large deviation functions in aggregation, and a problem that has been studied for many years. So this is me, and I am from IMSC Chennai, and I've been asked to advertise that there's a Homi Bhabha National Institute in Bombay to which we are affiliated. And our rating was going low, so we were told that we should have visibility. So the talk will be based on these two, a paper with on algorithm with Rahul Dandekar, who's right now a postdoc at Cycle, Subhashri, who's done most of the work, she's in the audience, and Oleg Zabronsky, who's in Warwick. This is published. And this one we thought we would put in archive before the talk, but we couldn't manage. So aggregation is ubiquitous. So I'll flash a few examples to show that at different scales, from planetary scale to micrometer scale, you see aggregation. So this is a satellite image of river Cam. These are the mountains, and these are it goes to the ocean. And if you think of these tributaries as random walkers, they're random walkers that go, and when two rivers meet, they aggregate. Okay, so this example is Saturn rings. They're made up of rocks and ice, and the dynamics of these particles are when they collide, they sometimes fragment, and sometimes they aggregate. So if you have a model with aggregation and fragmentation, you're often able to reproduce the mass distribution of Saturn rings. This is snapshots of cancer cells in vitro. They're quite mobile, and if you start them in monodispersed initial conditions, after some time, they tend to aggregate. And I do not know what they do the functionality, but they do tend to aggregate. Photographs of soot, they form fractal structures when allowed, they do aggregate. Finally, some examples from, this is SEM images of a material undergoing fracture. Ductile material, you have these voids, and the damage grows by these voids coalescing. And this is a simulation of charged polymers. When the epsilon permittivity is made suitably tuned, they start aggregating in this fashion. So aggregation is seen everywhere, and therefore understanding aggregation, people have tried to understand for a very long time. So I'll give some historical background and then state what the problem we are trying to do. So in these examples, there are two features. One is transport that brings clusters together, and then when they come nearby, they aggregate. So there are two kinetic processes. So there are two modeling options also. One is model both of them separately. So for example, you put diffusing particles, and when you meet, you put a reaction rate for meeting. Or you can combine these two processes into an effective collision kernel. So for example, if I look at ballistic transport, then two particles or two clusters with velocity v1, v2, the collision rate is proportional to the relative velocity and then the area of cross-section. So that is R1 plus R2. These are the radii to the power d minus 1 dimension comes here. Now, I will discuss this latter modeling approach. That makes the model simpler. So there's one model which I will call cluster-cluster aggregation. It's often known as the Marcus-Lushnikov model in the math literature. So you have a collection of particles. The particles have assigned a mass, m1, m2, m3, and so on. And the only thing they do is when you pick up two particles and they aggregate to form a bigger particle, conserving mass, I and j, this should be I and j, sorry, conserving mass, and there is a collision kernel that depends on the masses that collide. So right now, an arbitrary collision kernel, which depending on the physical process you study, you can choose appropriately. So once you incorporate the transport into the kernel, there is no space. This is a mean field model for aggregation. It works well in higher dimension, but for quantities like mass distribution, even in low dimension, it works very well. So the initial condition is all particles of mass 1. Number of particles is capital M, which will be a parameter. Mass is conserved, and every collision decreases the number of particles. So just to say, the initial, I had written this in terms of there is no mass here. It's easy to convert this into mass. So I'll give an example. So this is ballistic transport, the relative velocity, the radii. So this in kinetic theory, for example, is approximated by the square root of the moduli, the square. And radius for a spherical particle is m to the power 1 by d. For a fractal particle, I could have put a df here. And then if you assume momentum conservation, these become 1 by m. So it is possible to make mass-dependent kernels even if the original process is something else. So now I'll give a brief what has been the approach up to now. So there's a lot of history starting from Smolkowski equation from 1917. So what is that equation? It's a simple equation that enumerates how many ways can you create a particle of mass m, how many ways can you lose a particle of mass m. So if I enumerate, I have n of mt is the number of particles of mass m at time t that can change if another particle of mass m1 collides, and then there's a loss term. It can gain when two particles collide to create a particle of mass m. Okay, so that is the equation. And this equation appears to conserve mass, which is what we would expect because every collision conserves mass. Indeed, if you multiply by m and integrate and sum over all m, that gives you how does mass change with time. Then this delta function gets replaced by m1 plus n2. Here I just substitute by m and sum over m, and you can see these two terms are equal, and you get 0. But this is not always true. Even though this equation says it is true, is not always true. Why is that? So let us define one quantity, a current, which is the mass flux from mass at most up to m to masses greater than m. So this is whenever the collision involves a mass smaller than m and it creates a mass greater than m, then there is mass flux across the scale m. So for example, the definition is this one. So you have particles of m1 and m2 colliding. m1 is less than m or equal to m, but m2 is such that when m1 and m2 collide, the aggregate is greater than m. So this is some current, mass flux. Then that equation for d by dt of m times n of m can be written in terms of the mass fluxes as j of m minus 1 minus j of m. And if I sum over all m, then all these terms cancel 1 by 1, and you get a j of infinity, which is you assume to be 0. But mass is conserved only if this current at infinity is 0. But it is possible that if you have a mass sitting at infinite mass and masses go from A to B, then mass conservation can fail, as I'll show an example later.
Smallest question that you wrote. So that is, as if you have a finite number of particles, after some time there will be just one particle.
Yes.
Right? And then you cannot write this equation anymore.
I know. So this, the equation is being written for infinite system.
So
It's written for infinite
you
system.
assume that it's only a two-body collision, basically.
Yeah, only two-body collision, and for infinite. This equation has been written for M, that capital M going to infinity. So a lot of things are known about the solution for the small source equation. So let me give a quick summary about what is known. So in the cases where mass is conserved, you can write a scaling solution for the mass distribution, which is there is a typical, you assume there's a typical mass scale M of t. Then you have a prefactor here. If I put a power 2 here, then total mass is conserved, which you can just check by integrating with m n of mt. Then if you plug this back into the small source equation, there's a beta that's written here. So I define a homogeneity exponent beta. Many of these things are not important. I'm just giving a background to show that a lot of things are known. These kernels are characterized by one exponent, homogeneity exponent beta, which says what is the scaling exponent with m. So if I scale the masses by h, how does the overall kernel scale with h? That's h per beta. For example, if it is m1, m2, your beta is 2. So you plug this back into the small source equation. You can obtain a scaling for what is m of, how does m of t scale with time? In fact, it scales as t to the power 1 by 1 minus beta. However, you cannot compute this scaling function f for an arbitrary kernel, but for a few specific kernels, people have calculated. Yeah, yeah. So the other details don't matter. Only this homogeneity exponent matters in these solutions. So there are three solutions possible for the small source equation. One is the constant kernel, where the collision rate is independent of the masses. In this case, your m of t goes as time, and you can find the scaling function. Then there's a sum kernel, where the collision kernel is proposed. It's a sum of those two masses. Here, the typical mass grows exponentially with time. And then there's a product kernel, where you find that mass is not conserved. Okay, so product kernel is, the kernel is proportional to m1, m2. So here is a simulation. The small source equation can be solved to find the scaling function, and there's an expression you have for the mass distribution. But if you ask what is the second moment of mass for this distribution, it diverges at t equal to 1. And this divergence, this singular behavior is often referred to as a gelation transition. So this, you can do simulations. Just out of the m particles, you make them collide with these rules, and you measure the mass distribution various times. So here, we have just plotted the mass distribution at t equal to 0.5, which is this purple line. It is exponential. Then at t equal to 1, where the divergence occurs, there's a power law, 1 by m to the power 5 by 2. And beyond that, when you do simulations, there is some factor, some behavior here. And there's a gel type. A lot of mass is at large mass. Okay. If you do for tau equal to 4, this particular thing keeps going down, and this aggregate keeps growing. Okay. Now, this solution works well up to tau equal to 1, and beyond that, it does not work. The solution breaks down. Then there's a remarkable solution by Lushnikov, where he finds that for a finite mass system, he writes down a formula for the mass distribution in terms of some polynomials called Mallows-Riordan polynomials. Okay? So it's a complicated expression like this. But if you plot with those simulation I showed, it reproduces some curve like this. I find this quite remarkable because rarely is there a function that can capture a complicated behavior where things go down and then go up and come.
What is being plotted here?
This is this formula, and this is this simulation data for tau equal to 2. So it, huh? This is for the product kernel. Product kernel. The solution is for the product kernel. This. Okay.
Why don't you have load points everywhere?
Because in a simulation you cannot get 1e this probability. That depends on the we have done 10 to the power 6 averages or something like that. The previous slide was some Monte Carlo simulations for product kernel. This is the solution that works up to tau equal to 1. But this formula works for any tau, any m. I mean, it's okay. Gelation bit, and how these things go down. Everything is the formula gets. Capital M is the total mass. Yeah, it is proportional to it is a proper condensate in the sense it contains a finite fraction of capital M.
But here you said capital M is finite, so in that case, Smoluchevsky equation will not hold after some time.
No, so that is what. So this solution is for the Smoluchevsky equation for M going to infinity. But for a finite system, so there's in that particular case, there is a mass that vanishes. Now you ask, where does that mass go? So now if you look at finite systems, you can see that it's an aggregate that forms, and then you can solve for this problem. That is the thing. And so the exponent of the power is 5 over 2. But unlike some other models, it doesn't remain 5 by 2 beyond tau equal to 1. Here it goes back to some other distribution. So it's only at that tau equal to 1 that it is 5 by 2. Yes. No, it is a exponential distribution, and that cutoff goes to infinity at tau equal to 1. It is like 1 by, I forget. Yeah. So there is, in these, you are saying about this purple curve. As it comes bigger and bigger, so there is a behavior for m less than m star where it is 5 by 2. Then it crosses over to another exponential decay with some other power. I don't know, maybe 3 by 2 or something. I do not. Yeah, I agree.
So as t goes to infinity, everything is in the condensate?
In this case, t going to infinity, because we have finite system, everything is in the condensate. Okay. So this is, to summarize, so the Smoluchevsky equation, there is a phase diagram like this people have obtained. This is a review article. So for a particular kernel, which is the form m1 to the power mu, m2 to the power nu, and this particular form has some significance. Mu plus nu is what I called beta earlier. So if I put mu equal to nu, this line is like beta. Or every line like this corresponds to a certain beta. So in this curve, the 3 kernels I showed corresponds to this point, this one, and this one. Here there is no gelation. Some kernel also has no gelation. This is the product kernel. There's a gelation at finite time. Then you can give arguments to show that in this whole region, there is gelation. That means a condensate forms, but at finite time. In this regime, there is no gelation, a typical example being constant kernel. And the sum kernel is the boundary between no gelation and a place where there's instantaneous gelation. The moment time is started, there's an infinite aggregate that forms. That is instantaneous gelation. Here, everything forms a gel in the small Chaucer equation. In a finite system, that may not be true. Okay. Now, even though a lot of things are known, to my knowledge, the question about what is the probability of rare events does not seem to have been addressed within aggregation. So, so despite the long history, now there may be just a theoretical interest in there's a question to be asked, one could ask, but also, you know, in your many illnesses you have, like for example Alzheimer or mad cow, they form when an irreversible aggregate forms in your brain. Now you'd like to know what is the probability of that aggregate forming. That may be a rare event, so it'll be interesting to know whether that probability is low, high. This model is a starting point for that. So what is the question we like to ask? So if I look at the mean number of particles as a function of time, n of t is the mean number of particles, there is a typical trajectory it follows, the black curve. I could ask, what's the probability of the red curve? Okay, I go somewhere else far away. At a fixed time, I have a different number of particles, different from the typical. So the question I'd like to ask is, what is the probability starting with m particles? You have n particles remaining at time t. Okay, probability of n particles at time t. Likewise, I could fix this number. Then there's a typical time that particular density is reached, or typical number is reached. I could ask, what's the probability of reaching that number at an earlier time t? This one I'll call as p tilde of m and t, probability of this collision occurring exactly at time t. This definition is slightly different, but in the large m, large n, the answer becomes the same. But I just make a distinction to make sure that these two probabilities are integrable to one. So this is the main the quantity I'd like to find out. What is the probability of having n particles at time t given capital M? So the remainder of the talk, I will present a numerical algorithm that works for any kernel, and then results from an analytical approach for these three kernels. Okay. So to find probabilities of rare events, there's quite a well-known system of biased Monte Carlo simulations or importance sampling, in which so I give a brief example in the context of random walks. So this is x and t. I couldn't get a good random walk picture, but this is a random walk that starts at origin and reaches at some point x. You would like to ask the probability that typically x is order root t, but I would like to ask the probability of finding it at a point which is atypical. Then you weight this entire trajectory with a weight e to the power wx, for example. Now, keeping this trajectory fixed, you modify a little bit, for example, by changing one random number somewhere. So that changes the displacement at one particular step. That changes the final displacement to this red curve here. So now you have two curves, two trajectories, and you choose between them based on this weight. So it's like doing equilibrium simulations between non-equilibrium trajectories. Okay. After you find the distribution for x, then you unweight the bias. We would like to follow something similar for the aggregation, but aggregation is a complicated system, so how to implement this for that is a bit complicated.
So Rajesh, if you assume metropolis moves, in some ways you have assumed a steady state?
No, this is metropolis move between trajectories. Not the trajectory evolution is non-equilibrium, could be, but the movement between trajectories is metropolis. If you weight wx, x is the end point of this trajectory. So now, so let's look at aggregation and see how we can implement such an algorithm. So I start with m particles of mass 1, then two of the particles of mass 1 can collide and become a particle of mass 2. But then there are two branches, depending on whether two masses of two ones collide or one collides with the 2. And then this graph keeps going down and keeps expanding. Okay. So in addition, so the configurations are like a directed graph. Then there is waiting time between configurations. And there's also the parameter, how many configurations do you, collisions do you consider? Okay. A particular trajectory is you choose one directed path from the top node to the bottom node. For example, these blue lines like that. Now I want an algorithm that says, how can I flip from one trajectory to another trajectory? So I want a local move, a local transformation of the trajectory. For example, I'd like to change this configuration, keeping the rest of the trajectory fixed. So in this graph, if I can find an alternate path from here to here, or from here to here, then I can modify this directed path, keeping most of it same, but modifying only a little bit. So for example, I can replace these blue lines by this green or by this red. So I can transform locally along these loops. So then you can ask whether the loop interchange move is ergodic. So we can prove ergodicity of this local move by showing that any trajectory you have can be transformed into a standard trajectory through only such reversible moves. Okay. So this particular local move makes the you can go from any trajectory to any other trajectory. Then you can bias the simulations by attaching weights to either collisions or time. So in addition to modifying trajectories, you have to add and delete collisions. You have to modify the waiting times. All these things are kernel independent, and you can make it mostly rejection free. So the algorithm works, even though it looks complicated, it works reasonably fast and well. So now we wanted to benchmark this algorithm, and one way of benchmarking is with one exact solution. So the problem we can solve exactly for P of M and T is the constant kernel. So this is because, you know, I can just ask, I want to put up to T collision, at to T time, M minus N collisions, and then that just becomes some, you know, the probability of each collision with a delta function constraining the times. So if you do Laplace transform, inverse Laplace transform, you get some complicated formula like that. So if you plot the simulation answers with these exact answers, they match perfectly well, and you can generate probabilities of 10 to minus 40 or even 10 to minus 100 without much difficulty. Okay.
W is not important. Any value of W?
No, so you keep biasing W to get more and more rarer events, meaning going further away from the typical.
How do you do that?
You simulate for various W's and then patch these results together. So that is why these curves look a bit odd here and there, because we have not smoothened it, like this blue. Somewhere, when you join them together, like here. Therefore, different biases, and then they don't join meaning they do join well. We have not removed some of the data from there. Okay. Okay. So we needed these. So one was to create an algorithm which is kernel independent. The other was that these results from here helped us a lot in finding some analytical solution. So now I'll move to analytical solution. What can we obtain analytically for this problem? So I'll first state the results, then give the outline. So for an arbitrary kernel, we can show that if I look at this probability distribution, it has a large deviation form where m plays the role of rate. Okay? So we can write this as e to the power minus m, a function of n by m, which we call as phi, and m times t, which we call as tau. Okay? So this particular, this is independent of kernel. For every kernel we can show this.
So m is the probability of having
m is the number of particles in the beginning. So m goes to infinity, the deviation from the smallest associate goes less and less. So m is the rate. Then we can obtain exact expressions for this function f for the constant sum and product kernel. Also, we can obtain exact expressions for the incident trajectory, not instant, the incident trajectory, the trajectory that maximizes the particular constraints we put in for constant and sum kernels and some regimes of product kernel. So it also turns out that for the product kernel, this particular large deviation function has a singularity in that the second derivative has a discontinuity. Okay? This is probably because of the fact that for this kernel there is a gelling event, and that shows up in this large deviation function. So now let me just write down some answers. So for the constant kernel, if I look at the n is the number of particles, the incident equation looks like this. dn by dt is minus n squared by 2. If I didn't have this e, this looks like regular aggregation without for a constant kernel. E is a parameter which gets fixed with these boundary conditions that you put in. So you are starting at time 0 with number of particles 1. At time tau, you want the number of particles to be 5, which is the constraint we are putting in, and that fixes E. Then the large deviation function has forms for a certain behavior for small e equal to 0. E equal to 0 is a typical answer, and that the large deviation function goes to 0. And there's a lot of phi, log tau terms coming here and there. And this particular expression matches perfectly with that exact answer which I showed before, from which you cannot read out a large deviation function, but we can now have a formula for that. And then if I look at this incident trajectory, it matches perfectly with the simulations that we did with that algorithm we showed before, I showed earlier. Okay. So this is more simulations. So this is with keeping phi fixed, changing tau. This is keeping tau fixed, changing phi. And these are those figures got reproduced. I'm sorry, I was bit. And this is the incident trajectory. So it seems to work very well, this calculation and this one. For the sum kernel, we have an expression for the incident trajectories, where E is again fixed by the condition that at tau it is phi. The large deviation function has a simpler form. For large tau, it goes as tau phi by 2, and for small tau, it is a power law behavior, and so on. And again, if I look at the simulation answer for the large deviation function with the exact answer, it matches very well. This is with fixed phi changing tau, fixed tau changing phi, and this is the instanton trajectory for that. For the product kernel, it becomes very complicated to solve. So what we have is an expression for the large deviation function with an unknown function g of phi, where g of phi is maximizing an expression that involves those complicated polynomials which Lushnikov solutions had. This we cannot compute exactly in closed form, so you have to evaluate numerically exactly this particular maximum, plug it back in here, and then if I look at the large deviation function, it again matches perfectly well with the simulations. And there is this is with fixed tau, fixed phi changing tau, this is fixed tau changing phi, and there's another curve here which we have plotted, which is a calculation based on a different scheme we had, which seems not to work. It works for some phi and doesn't work for some phi. It is not that important. We do not have an equation for the incident solution. So what we have shown here is you solve this for various tau, find out where does phi become minimum, then you plot that where the minimum comes, you plot against tau, and you compare with a regular typical Monte Carlo simulation. And so what this shows is that from the exact answer, if you track the point at which it becomes minimum, it actually matches with the typical trajectory. Okay. And this is the singular behavior. So if I look at the second derivative of f, it has a jump for tau greater than 1. It has a jump singularity, discontinuity at that point. This is for finite m. If I change m, some features change slightly, but not for so much. So quickly, what is the method of solution? So we start with the master equation for aggregation. We follow what is called the Doi-Zeldovich procedure, introduce annihilation operators, creation operators, rewrite as a Schrodinger master equation as a Schrodinger equation, and derive an effective Hamiltonian. Then you introduce coherent states to derive an effective action, which looks like this. Some complicated form, where there's an E here, which is the energy or the Hamiltonian, which is the constant of motion. Okay. Then you find out the Euler-Lagrange equations. So there is the two variables z and z bar. They all have index m. One of them has a boundary condition starting at t equal to 0. One of them has boundary condition starting at t equal to infinity at tau. They're a bit complicated, but it turns out with some difficulty one can solve them. Then you evaluate this delta function using saddle point method. So I have skipped this. It is if you follow this procedure, you get the answers I wrote before later. Okay. So let me just summarize. So aggregation, unlike diffusion or something, or a few species system, is an infinite species system. Each of those masses is like a different species. We are able to calculate the large deviation function for standard kernels, and this goes beyond the usual paradigm in aggregation. Then there's LDF is singular for product kernel, so we expect it to hold for other gelling kernels also. But in these calculations, I showed that plot with method 1 and method 2. So the different ways of there are different ways of deriving the action, and we find that different actions can be got and corresponding to that different LDF, especially for product kernel. Then we have to make a choice based on what is a better guess based on simulations, as well as what gives us Lushnikov's answer. So there's some ambiguity there, which is not so in this derivation. Usually this ambiguity is not appreciated, but I think there is some issue there which one doesn't. I don't know what the solution for that one is. What I didn't mention was that we can determine the mass distribution along the trajectory from the incident trajectory fully. Other questions we have been trying to interested in is what is P of m1t? What's the probability of having all the particles gelling at any time t? What is the probability of fluctuations about the incident trajectory? What is the LDF when there's an input of particles also in addition to aggregation? Can we generalize this to collisions which are not binary but k-nary, and look at other kernels numerically, for example, somewhere here, somewhere here, somewhere here, and so on. Explore this diagram, phase diagram numerically. So that is
questions, Sumedha?
Yeah. So can you go to the sum kernel slide? So your f of phi tau here has a form where the last two terms look like the large deviation function for a random bit, and then there's a rest of the term. Is it a coincidence or?
I do not know. There's a formula the derivation gives. I have no idea. Because in these calculations, a lot of Stirling formula approximately. Maybe it is that. But is there a connection to some other?
Because it was not there in the product kernel.
No, product kernel, as I said, it has complications, and so it turns out that for the product kernel to find the large deviation function, only thing you need to know is the typical solution, Lushnikov solution. Mm-hmm. The typical solution is enough to find the answer for the large deviation function, which is very strange. There is some structure in the equations. I do not know what that is. Okay. So you don't have to know what's the incident solution, whether we are looking at various phis or not. So it is some strange some strange simplification occurs for the product kernel.
Other questions?
Hi, Rajesh. So I have two questions. One, in that trajectory-based importance sampling, how do you choose the tilting parameter lambda in the simulation?
In that, so this move where you do this loop exchanges, that is just to change, keeping everything else fixed.
Right.
How can I go from one trajectory to another
to the other.
trajectory?
But
Then there are waiting times between each of these collisions.
Yes.
So I can ask, so there's a final time at some point here, there's a final time. I can bias that time with e to power wt up and 4. Or I can say, so this is for example 1, 2, 3, 4 collisions. I can add a new collision here, delete this entire collision here. So I can weight the collisions with a w and make this graph go up and down.
Okay.
So I can, so we do both weighting.
Okay. And my second question, can I ask?
Yeah, quickly.
The second question was that you had this singularity in the last division, and typically those singularities corresponds to switching of instanton paths. Have you seen that in your this kind of optimal solution method, saddle point?
No. The okay, so let me now show that. The incident solutions in some regions of phi where the singularity was not present. This I'm just guessing. There's a straight line from here to wherever it goes. So there is that. There's a formula we can derive for that formula. Beyond that, there is some deviation from that particular curve. There's a switch from that particular solution to another solution. Is it connected to that or not? We do not know. But we do have, so you can see, for example, this curve, there's a straight line here, and then there's a deviation at some point. So we do, so that is all I can say.
Yeah, so probably I missed that, but what is the different physics for the different kernels? I mean, why do you use that kernel or another time another kernel? What is in there?
Oh, so we would like to have a formalism for any kernel, but these three kernels happen to be solvable. Now,
is there no physics motivation?
oh, there is physics motivation also. Yeah. So for example, if I look at how proteins aggregate, the product kernel seems a good one because particles of mass m1 and m2, they sometimes, if I have a diffusion or networks that collide, product kernel seems useful. But if I have some system where the diffusion constant increases with mass, then the addition kernel is a useful one, and the constant kernel has some other. So all these things have been looked at.
For example, if I want to know aggregation for active particles, what kernel would you recommend?
I can't recommend that. No, not in that sense. I can't recommend. That is for people to ask a kernel and plug it into the formula.
Well, but before you plug formulas, maybe.
No, so the active particle, if you look, so you have to have some idea of the transport and have some idea of what kind of clusters form post aggregation. For example, they might be fractal. Some of them are compact. Some of them are compact. Some of them are don't grow in size. So you have to look at the physical system and look and then make a possible guess for. So for example, this polymer problem, you may have a rod, but the rod is rotating a lot, then it becomes like a sphere. So you have to make a guess based on your intuition. Or intuition, I mean, you have to look at the problem and answer.
So Rajesh, let me ask one question is, I mean, if you look at in 1D, for example, and you again have this mass collision, just diffusion and aggregation, let's say. So there we know that M typically will grow like t to the power 4/3 or something on the other end. So can you calculate this objective probability distribution of the mass?
So that's also in the outlook. What happens here is in this action, in addition to this term, there will be del z bar square kind of term.
Right.
So when you write when you write the Euler-Lagrange equation, you get a diffusion term in addition to the del square phi, a diffusion term. But then you have something diffusing from time t equal to 0 to t with x, and then the boundary conditions for this z, what we are called y here, is defined at time t equal to 0. Boundary conditions for the other one defined at time t equal to tau. And then we have to find some matching solution. So we'd like to do that, but we have been stuck with this for some time. So now,
You can do on a lattice. On a lattice, you can do solve it exactly. This was Jultan, Ruck, and other people had done that. I mean, you can set up the recursion relations.
yeah.
Perhaps, I mean, that's a different way of solving it.
In fact, so we would like to say that if we can find a formalism like this that works, then we'd like to compare with something that is
Yeah,
known.
sure.
And
This
then
is a big continuum version
Yeah.
of that, basically. Okay, so are there any other questions? If not, let's thank Rajesh and also Ms. Tansi, and we'll come back here at 11:30.